So by definition, a rational function has a numerator and a denominator. It's written as a fraction, and so it naturally has an issue with the denominator. So we know anytime we have something of this form, a rational function, it has an issue in the denominator because we can't divide by 0. So if I'm looking for things that x is not allowed to be, I would go ahead and say, well, x minus 5 can't be 0, so we would find what we call excluded values, that this function has an excluded value at x equals 5 because x is not allowed to be 5. And then that works hand in hand with the domain, because if x can't be 5, we can either write the domain as x is not 5, which would mean it's everything else except for 5. We can plug in anything else. Or we can write it in interval notation, where we're saying that the domain goes from negative infinity to 5, but doesn't include it, and then from 5 to infinity. So we're saying same thing as we were saying there. We can use every x value except for 5. Okay, so that's something that we're bringing into this, but knowing that there's excluded value at 5, there is a domain where we can plug in anything except for 5. What we're answering is what is happening at 5. If I can plug in anything else for this graph, any other x value, and I have graph there, but then I can't have graph at 5, then something has to be happening there to help us graph this and know more about what it looks like. So anytime we have an excluded value, it has to be either a whole, which means I have graph to the left and the right of that specific point. They're very tiny. It's just at that one point. We're going to graph them like this, where it looks a little bit larger, quite a bit larger than it actually is. If you're looking on a graphing calculator, you can't see it at all. You would have to zoom in a ton to be able to see it. But if you trace that x value for this one, if you traced at 5, it would say undefined for the y value. Or we can have a vertical asymptote, which is just a guide for our function, that it is going to be to the left and the right of our vertical asymptote, but it's going to serve as just a guide that it will avoid that value, in this case at x equals 5. It will avoid 5. Okay, so every single time we have an excluded value, it has to be a whole or a vertical asymptote. So now, back to our original, how do we decide whether this 5 is a whole or a vertical asymptote? So that brings us to our rules for that. It all comes down to simplifying. So if I simplify, and we have a factor that gives us an excluded value does not cancel, then it automatically is a vertical asymptote. So if we can't simplify it, that factor doesn't cancel, it's a vertical asymptote. If the factor that gives you an excluded value does cancel, then it's a whole. So if we're looking at this example, I don't know if I can show us these at the same time, I'll just put it over it. If we're looking at this example where we're talking about x equals 5, we're looking at the factor x minus 5. I don't really care about any other factor here canceling except for the ones in the denominator. Those are the ones that give us excluded values. So if that x minus 5 can cancel, then it's a whole. If it doesn't, it's a vertical asymptote. Note that if you've got things added or subtracted, they are grouped together. So x plus 1, I like to call it a chunk. X plus 1 is together and x minus 5 is together. So unless I can cancel the whole x minus 5, I can't cancel anything. Don't cancel here. That is not allowed. So if we can't factor anything out, then we can't cancel anything, and in this case we can't. So this at x equals 5 would be a vertical asymptote. So didn't cancel, automatically a vertical asymptote. Okay, what it could look like, we could have a situation like this, where in this case I have more than one excluded value. I've got that x squared minus 7x minus 30 that can't be 0. So I'm going to have two different excluded values whenever I factor this. Let's see, we've got x minus 10, x plus 3. And then in solving, we get that x can't be a positive 10, and x also can't be a negative 3. So I have two different values that I'm trying to determine. Each one of these, every single excluded value, is either a whole or a vertical asymptote, so it has to be one or the other. So I'm going back to my original function and trying to decide if either of these are going to cancel. So by our factoring, we can tell that one of them is going to cancel. So that x plus 3 will cancel with x plus 3 in the numerator. So this tells us that my excluded value, x equals -3, or that we can't have -3, is a whole. We've canceled it. That at 10, we're going to have a vertical asymptote. It did not get canceled. It's a vertical asymptote. If it gets canceled, it is a whole. Now we can go a step further from this. So our vertical asymptote, we'll go ahead and give the equation for that vertical asymptote. So since it's a vertical line, we'll say x equals 10. So that's our vertical asymptote. For the whole, I do want a point. So we're saying that we have a whole at -3 is the x value, but we also want a y value of our whole because we are going to go on to graphing these. So now with my -3, I couldn't plug it in before because that would give me 0 in the denominator. But once I've canceled and I have this simplified function, I have canceled that whole. So now I'm able to plug in -3 and get that f of -3. This is the place where that whole is at, my -3 minus 10. So it is at -3, -1/13. That is where the location of the whole is. If ever you're trying to find the y value of the whole and you plug in the -3 into the original, you will get undefined, and hopefully that will let you know, oh yeah, I can't plug it into the original. I have to go to the simplified and plug in my -3 here. That's where I can plug it in. A vertical asymptote can never be plugged in, so that might be a clue as well to the fact that something is a vertical asymptote, because it doesn't get canceled, and so I can't plug it in the original, and I still can't plug it in here. Okay, so a few more examples with that. Let's look at this guy. So decide what your excluded values would be. Let's see if I can use the back of this. Yeah. So since our denominator can factor into an x plus 4 and an x minus 4, that means our excluded values are going to be a -4 and a +4. And anytime we have the same number but different signs, this can be a little bit tricky because we have to keep track of what excluded value came from that factor. Because now when I'm deciding what they are, my x plus 4 cancels, but the x plus 4 gave me an excluded value of -4. So when I'm deciding, okay, it canceled, so that means that I have a whole there. We have a whole at -4 something, because it was the x plus 4 that gave us the excluded value -4. So that can be a little tricky. And then we know that we do have a vertical asymptote. Our equation, vertical line, would be x equals +4. That is the excluded value that came from x minus 4. And then our last step is finding that y value of the whole. I can plug in my -4 here, and again, if I tried a +4, it wouldn't work because it's a vertical asymptote. So plugging in my -4 here, I get -1/8. Okay, last one. Go ahead and find your excluded values. It's going to be a little dark, but I think it'll work. This will take factoring the denominator. While we're at it, we might as well factor the numerator because some canceling. Let's see, -3 to -4. So we've got excluded values at 3 and then a +4, both positive. Notice that neither of them cancel. I don't have any change. So that means that I don't have any holes. And so nothing cancels. I don't have any holes. That means that we'll have vertical asymptotes at x equals 3 and x equals 4.